2022. My project is over the physics of active longitudes and their impact on Earth through the interplanetary coronal mass ejection they produce. Even though my major is mechanical engineering, my project is still through the physics department, and my mentors are Dr. Bahim and Dr. Ramashitz. The goal of this research will help us understand the role of active longitudes in solar atmospheres that lead to formation of interplanetary disturbances, which can cause strong geomagnetic storms upon arrivals to Earth's orbit. Our hypothesis is that it is possible to find a set of criteria which can tell when an active longitude is a potential danger, so it can form a geoaffective interplanetary disturbances. The summary of our project is the solar source of interplanetary disturbances, which caused the strong geomagnetic storms in 2005, were located far from active longitudes. This is new and unexpected results. Usually recurrent severe storms associated with the same active region on active longitudes or different active regions in the vicinity of active longitude regions. The phenomena can be explained by the sharp drop in solar activity in 2005. Sunspot number decreased from 200 in the beginning of the year to 50 by the end. What's addressed is relative position of active longitudes with respect to the Earth's project onto the Sun, the anomaly in the longitudinal distribution of active regions themselves. It is often referred to as active longitudes in order to reveal the connection between AL and CME spatial occurrences. Here we investigate the morphological properties of active regions. What could have been addressed but hasn't because it's not directly related to active longitudes. The area of solar atmosphere covered by open field lines in the vicinity of active longitudes. Rossby waves. The Rossby wave can arise in the action transition layer at the bottom of the convection zone and can produce large-scale, long-duration deviations from a regular differential rotation. This can lead to global magneto-hydrodynamic instability. And this is a graph of the Rossby waves. These three graphs are in a span of 40 minutes, and you can see it covered 3/4 of the sun. The AP index is the earliest occurring maximum 24-hour value obtained by computing an 8-point running average of successive 3-hour AP indices during a geomagnetic storm event and is uniquely associated with the storm. The involvement is the AP index provided a daily average level for geomagnetic activity. We measured the geomagnetic activity to predict geomagnetic storms. The method is that we took the average AP for the day. Originally, we did 20 but upgraded to 50. 20 shows small disturbances in the geomagnetic field, but 50 is severe storms. Then we located the storms and determined if it affected Earth. In the top graph, we have the AP every 3 hours measured for the year 2005, and at the bottom we had the sunspot numbers in 2005. As you can see, even though there's a sunspot number, it doesn't mean that there is a high index for the day. Just because there's a cloud doesn't mean that there's a storm. And here's a better graph so you can see the line. And here are the AP values that we took. The red lines are the AP values that are above 50. It doesn't affect people directly, we cannot feel it, but it'll blow up transmitters, affects NASA, and in March 1989 we had a 9-hour outage of Hydro-Quebec electricity transmission system. So this whole area, the black area, was out of power for 9 hours. And the storms we selected here is June 18th. As you can see, the black spot is the sunspot. And here is an H filter. It just shows it a little bit better, and you can see some solar flares there. And here's the 19th of the same month, and here's a little zoomed in of the region. And again with the filter so you can see better. And this is how we determined where the storms are. As you can see, there's a very active region right there on the 15th. And if we go down a slide, we can see that that is about 180 degrees. So the credentials that we have is Buczynski and his team made a claim. In this project, we will study dependence of solar flares' geoeffectiveness on their position in terms of the Carrington helio longitudes. It is found in Buczynski and collaborators in 1986 that longitude zones with active sunspot formation produce majority of the strongest solar flares and other solar activities. The predominance of solar sources in the longitude zones from 270 to 300 and generation of near-Earth disturbances of all class, including recurrent series of geomagnetic extra storms, were demonstrated in Ibnati et in 2002 and 2005. June 23, 2005, it was not the largest storm, but it was located closest to Earth. As you can see, the location was 250 degrees, which is not 270, but it's the closest to it. The activity on the sun took place on the 20th, but on Earth's time it was June 23rd. Sadly, we do not have pictures on June 23rd because it's hard to take pictures during the storm, and there's other events on Earth, such as our own storms, so it's hard to take photos, and in 2005 there weren't the best pictures. So how we know the location is observed by Probatube in Belgium. As you can see right here, this little red dot, that is the storm. And on this graph, if we go under 23, we can see that it is about above 250. So that is the closest. In the graphs I was talking about earlier, on June 18th and June 19th, that is also another way that we can kind of tell where the spot is. If we look at these graphs and we can determine where the spot will be in a few days. And thank y'all for your time, and thank you for listening to me.